Hello, we'll be doing another topic in chapter number 16, a subtopic where we are going to write the Ka-Kb expressions and try to relate what they mean. In order to do that, I'm going to share my screen so that we can follow it through. So let me go right on the top and then explain everything. So basic content for this particular chapter is that this section is Unit 3. We're going to write the equilibrium constant expressions for acids and bases, understand the relationship between Ka for acid and base and its conjugate base, calculate the pKa from the Ka values, and understand how pKa is correlated to the strength of the acid or base as respectively. We know that according to the equilibrium constant expression, we can write the equilibrium constant for a weak acid as the concentration of the products divided by that of the reactants. In this case over here, in order for a substance to behave as an acid, it must be a proton donor. But in the expression, we don't see the water molecule because the ionization of water produces very, very small amount of H3O plus and OH minus, so that there is hardly any change in the amount of the ions present in water, as per this slide. Then the relative, same way we can write the relative strength of an acid or base can also be expressed by its ionization constant, which is for acid or base. And now we have written the conjugate base and its expression that water will donate a proton to the base, forming an acid and release the OH ions, so that again water is present in large quantity and therefore we do not write it. Now for weak acids and weak bases, Ka and Kb are all have values that are less than 1. Acids with a larger Ka value are stronger than the ones with a weaker Ka value. Bases with a larger Kb value are stronger than the ones with a smaller Kb value. And this is important to remember, especially when you have to predict the direction of a reaction. Strong acids and strong bases almost completely ionize in water. They have 100% ionization even under moderate concentrations. Therefore, the K values are very, very much larger than 1 and hence considered as product-favored reactions. On the other hand, weak acids and weak bases ionize to a small extent in water, and so they are considered as reactant-favored reactions. Now, the equilibrium constants, the product of the concentration of the H ion and OH ion is Kw, which at 25 degrees Celsius is 1 times 10 to the power negative 14. If the temperature changes, then Kw will change. Now, this is a problem for you. Just try to solve it out. And here is a list of the acid ionization constants for the acids and their conjugate bases. And I want to use this chart to describe something important. A large value of K indicates that the ionization products are strongly favored, whereas a small value of K indicates that reactants are favored. The strongest acids are at the upper left of the chart. They have the highest Ka values. Ka values become smaller on descending the chart from top to the bottom, indicating that the acid strength decreases. The strongest bases are at the lower right, and they have the largest Kb values. Kb values become larger on descending the chart as base strength increases. Furthermore, the weaker the acid, the stronger its conjugate base. The smaller the value of Ka, this implies larger the value of Kb. Aqueous acids that are stronger than H3O plus are completely ionized. Even under moderate concentrations, their conjugate bases, for example, HNO3, the acid is very strong. The conjugate base is NO3 minus, does not produce any meaningful amount of OH minus ions, and therefore the Kb values are very small. And these ions will not impact on the reaction with water. And this can be the same explanation can be used for strong bases and their conjugate acids. Now, here is an example of equilibrium constants for some acids and their conjugate bases. As you can see, when the Ka is very small, the conjugate base value Kb is very high, and vice versa. Furthermore, when we look at water, water can function both as an acid and base. When a material can behave both as an acid and a base, we call this as amphiprotic. And there are many polyprotic ions that can behave as amphiteric ions, depending upon the reaction and the strength of the other Kb and Ka in solution. Now here, the auto ionizing, it is shown that if you look at the geometry of water molecule H2O, you see that it's a bent angular, and oxygen, if you remember your geometry from General Chemistry 101, you know that water has a tetrahedral geometry. Vespa theory suggests that water molecule has a tetrahedral geometry, indicating that it has 4 pairs of electrons, of which 2 pairs are used to bond with hydrogen atoms. The remaining 2 are lone pair, and it is the hydrogen of one molecule bonds with the lone pair on the oxygen, and you get your chain formed. And here, the pH, we have been talking about it, is like basic is, so the basic pH is 14. The hydronium ion concentration is 10 raised to minus 14. The OH ion is 0. And the POH is 0. So if you go across for acidic and basic, you will see that the neutral is 7. And the acid is, if the acid is 4, then the POH is 10. Because the sum of pH plus POH must be equal to 0. The sum of pH plus POH must equal to 14 and not 0. Now, how do we count? If the pH is given or the POH is given, how does one calculate the concentration in moles per liter of the respective ion? The solution is just take the antilog of the pH, and then you can get it, the answer. How do you write it? Basically, you put it 10 to the power negative pH, and you can find it, and same goes true for OH. The second thing is we know that the concentration of OH minus ion times that of the concentration of the hydronium ion is equal to Kw. This expression can be used to calculate either the concentration of the H3O plus ion or the OH minus ion if either one of them is given. In summary, here is what it is. Ka and Kb always have values that are less than 1 if they are weak. Acids with larger Ka are stronger than those with smaller Ka. Bases with larger Kb are stronger than ones with smaller Ka. Most acids and bases are considered as weak. Strong acids and strong bases almost completely ionize in water, giving rise to a product-flavored reaction. Weak acids and weak bases ionize to a smaller extent, indicating that the molecular species is present in a larger amount, and therefore it is reactant favored. The product of the value of H and OH depend upon each other, and they can be interchanged and used. And so Kw is equal to auto-ionization constant of water is 10 raised to minus 14 at 25 degrees Celsius. Now we go to the polyprotic ions. Now we will do this part in greater depth a little bit later on, but polyprotic ions, like phosphoric acid, they ionize in a series of steps. Remember that the acid and its conjugate base must differ by one proton. So you cannot take two protons in one step. You have to take it one at a time. And so the reaction is shown over here. The first H3PO4, when you dissolve it in water, will donate its first hydrogen, forming the dihydrogen phosphate ion. In the second ionization step, the dihydrogen phosphate loses a proton and forms the monohydrogen phosphate. And in the third step, the monohydrogen phosphate loses a proton and forms the phosphate ion. And from these reactions, you can say that the equilibrium constant, Ka, varies by a factor of 5 for when you compare each step with the one before it. So comparing Ka1 to Ka2, we see that Ka2 is 10 to the power negative 5 smaller than Ka1. And same thing goes for step 2 and step 3. Ka3 is 10 raised to minus 5 times smaller than Ka2. This indicates that in most of the cases, that in the very first ionization step, most of the hydrogen is lost, is removed by the water or donated to the water. And the reason why you have such low Ka values for the second and third step is because it is extremely difficult to remove a proton from a negatively charged ion than from a neutral molecule. Many inorganic polyprotic acids have values become smaller for each proton removed by a factor of 10 raised to minus 5. And here again, once again, you can see the concentration, increasing strength of an acid and its conjugate base, and increasing acid strength in terms of pK value. Lower the pKa value, stronger the acid. So that's some important point to remember. And then what happens if you have organic acids? You see that longer the chain, lower the pKa value, and if lower the pKa value, lower the Ka value, then naturally lower the pKa value. And you can see as the chain length decreases, the Ka increases, or the strength of the acid increases. The second question is this, that if the acid and its conjugate base, Ka and Kb, are taken of the same acid, then what is the result of the reaction or the ionization that is there? We find that when you do that for the same acid and its conjugate base, the product is water, and therefore we get an important relationship that Ka times Kb is equal to Kw. When adding equilibria, you multiply the K values. And with that, I'm going to stop the share and finish off with this part